This is the first example of ANOVA problems. The researcher wants to know if room temperature affects college students' math performance. So he decides to look at how well students do math problems under three temperature conditions: 50 degrees Fahrenheit, 70 degrees Fahrenheit, and 90 degrees Fahrenheit. And this is the result. No. Okay. And this is a setting. Because we can't compare the populations, there are too many college students in the world, so we use samples. We take 5 people from each sample, each conditions. Three different treatment conditions. And okay, 5 people. So we put 5 people in 50 degrees temperature room, and 5 people in 70 degrees temperature room, and 5 people in 90 degrees temperature room. Notice we have only 5, same number of people. That's gonna be kind of important later. When we create hypothesis, okay, this is mu1, mu2, mu3, and sample we use notations like m1, m2, m3, just like previous examples with comparing 2 groups. We just have 3 groups this time. And the data we got from this test is this. We had 5 people. This person got 0 correctly, and this person got second person in this room got 1 question correct, and this person got 3, and this 1 and 0 correctly. And this is the mean number of questions they got correctly. And 4, 3, 6, 3, 4, and mean it's 4 here. And in this room, 1, 2, 2, 0, 0, and the mean number of questions they got correctly is 1. At a glance, it looks like 70 degrees temperature is better than these two 90 degrees or 50 degree temperatures in terms of solving math problems. And what we can do with ANOVA is just to examine if there are any differences between these 3 values, 1, 4, 4. When we say difference in statistics, it means just a significant difference. So even if there's a difference, 1, 4, 4, these differences may not be significant. So in that case, we say, there's no significant difference, no difference or no significant difference. That's what we'd like to determine. How we do that, okay? Null hypothesis in ANOVA is like this, because we can't compare 1 and 2, 2 and 3, and 3 and 1 separately. That would require more than one null hypothesis. We just want to have one null hypothesis, and then the way only we can do it is just put all these 3 and together like this. And alternative hypothesis in ANOVA is saying that the null hypothesis is not true. This is a key point, very important. And alpha level, in our class, we decided to use 0.05 all times. As usual, I would like to know, okay, this is F distributions. F distributions looks like this. The reason behind this is because how F distributions are created. F statistics are calculated. Basically, F statistics calculated this way: between group variance divided by within group variance. Between group variance and within group variance, what are they? Okay. between groups variance is a variance between groups 1, 4, 4. Variance between these three numbers, three values. What about within? Within is just like in the previous examples, variance within group. This time we have 3. So comparing 3, we kind of calculate the within group for each group and add them up later. That's the within group variance. So why we do that? Between group variance divided by within group variance. What does that give us? What it gives us is that we could kind of figure out how big the between group variance is. That's what we're trying to figure out. Are these groups different from each other? What's the size of the variance between groups? To come up with that, we use the denominator. We use the within group variance as a denominator. If between group variance is larger compared to within group variance, there are much larger, significantly larger variances between the groups than the variance that exists within groups as a whole. If between group variance is the same as this standardized within group variance, then it kind of implies that between group variance is the same as within group variance, not so different. That means the variance between the groups is just like the variance within the groups. So this variance is, even though there's some variances between the groups, but that variance is not large enough. That's how we're gonna. That's the logistic behind it. And when you do that calculation, when you use the between group variance divided by within group variance, the distribution shapes somehow does not form the mountain shape anymore. It looks like this. It kind of looks like the hump here, It kind of looks like a y equals 1 divided by x kind of shape. Might have something to do with it. That I will leave it up to later video. Okay, so basically using this distribution shape, what we would like to know is, we'd like to know the critical point, critical region, and we'd like to, do F-statistic to figure out if certain value is going to fall into critical region or not. So basically the same thing. So we just have to know how to calculate F-statistic and also finding out the critical point, critical value of F. As usual, degree of freedom comes into play. Depending on degrees of freedom, the shape is going to be slightly different. Let's figure out the critical region first. And then how you do that is, we need to know degree of freedom between and degree of freedom within. Degree of freedom within is this side, and this is between. How do you get these numbers between group? Degree of freedom between and degree of freedom within. This is how you do it. Degree of freedom between is k minus 1. K is the number of groups. So if there are 3 groups, that means degree of freedom between is going to be 2. Degree of freedom within is n minus k. N is a number of entire sample groups. So there are 15 people in 3 samples in total in this example. Minus k is number of groups, so 15 minus 3. In other words, it's just like a degree of freedom of group 1 combination of sum of degree of freedom for of group 1, group 2, and group 3. Because 5 minus 1 plus 5 minus 1 plus 5 minus 1 is going to be 5. It's going to be n, the total number of the sample groups. And k is going to be 3 because subtracting 1 from each group. Then if there are 3 groups, then subtracting the number of groups, the same equals to subtracting 1 from each group. So this is going to be kind of easy to remember. So based on these, degree of freedom between in this example is 2, and degree of freedom within in this example is going to be 12. And that's how you get the F value. So here 3.885 is going to be about here, and if the F statistic falls into this region, we reject null hypothesis, concluding that there is some difference among the 3 groups. And as I said, F statistics is calculated by between group variance divided by within group variance. Between group variance is sum of square between divided by degree of freedom between. Why do we do that? It's going to be a different video topic. And how do you calculate sum of square between? This is how you do it. That kind of makes sense though. Anyway, that's going to be a different video. Based on this formula, sum of square between is going to be 30. Between group variance is going to be sum of square between divided by degree of freedom between, so 15 in this example. Okay, let's look at the within group variance now. Within group variance is calculated by sum of square within divided by degree of freedom within. And sum of square within is kind of easy. It's a sum of sum of square for each group. So we know how to do it already. Sum of square for the first group is 6, and sum of square for the second group is 6 and 4. So when we add them up, it's going to be 16. So sum of square within is 16. So within group variance is going to be sum of square within is 16, and degree of freedom within is 12. So 1.33. Coming back to the formula for F statistic, which is between group variance divided by within group variance. So 15 divided by 1.33, which is 11.29. 11.29 is going to be way over here, so it falls into critical region, so we reject null hypothesis at P is less than 0.05. That means there is some difference. I don't know where the difference is. Maybe between mu1 and mu2, or mu2 or mu3, or between mu1 and mu3. We don't know, but there is some difference somewhere. That could be 1 or 2, but they all could be different, or just one of these could be different. We don't know, but at least there's one difference somewhere. It could be 3 differences, because it doesn't tell us which pairs of mean differ, so we have to do a post hoc test to determine which pairs of measures means differ, and that's the next topic.